Hello everyone, welcome. Myself Preetham Kumar and I'm currently pursuing my studies at Karan Institute of Technology and Sciences, Coimbatore. In this video, I'll be presenting the coding component of Practicum 1 from the subject Computer Organization and Architecture. This section focuses on implementing unsigned integer arithmetic using MATLAB. The objective is to observe how different bit widths affect computation, overflow, underflow, and memory usage. I'll demonstrate each program by running it in MATLAB and explaining the logic step by step. So I would like to show my PDF which I prepared for the Practicum one. These are the sample programs which are given, and this is the procedure how we have completed this Practicum. And these are the questions and the corresponding outputs are given below down, and the outputs as well. There are totally 5 questions. I'll be explaining each of them in MATLAB. Let's begin with the first program. Program 1, unsigned addition for 8-bit or 16-bit and 32-bit. What this program does? This program performs addition of two unsigned integers using selectable bit widths like 8-bit, 16 bits, and 32-bit. The user enters two integer values, and selects the required bit width. When we go to the coding explanation, what is the first line? CLC clear. This clears the command window and removes previously stored variables to ensure a clean execution. The third and fourth line, these lines accept two integer values from the user. And the fifth one is here the user selects the desired bit width for arithmetic operation. And coming to this condition checks whether the user selected 8-bit arithmetic. If it is 8-bit arithmetic, the following condition goes on. That thing is the inputs are covered into 8-bit unsigned integers, simulating an 8-bit hardware register. And for the 10th line, this performs the unsigned addition using 8-bit arithmetic. And the 12th line, it displays the computed sum. This is just a print function. And the 14th line, this checks whether the sum exceeds the maximum 8-bit value, like the 255 or not. The sum is greater than 255, the 15th and 16th line displays an overflow warning if the limit is exceeded. Else, display no overflow in 8-bit arithmetic. And end. This is the line where the if statement ends. The line 21, info and the whos command. The whos command calculates the memory usage of variables. The same logic is repeated for 16-bit and using unsigned integer uint 16 and 32-bit using uint 32, where higher bit widths allow larger values and consume more memory. Now let's run the code, and if I enter the value as 23 and the second value is 32, and if I enter 8-bit, and it shows me the result as 55 and no overflow in 8-bit arithmetic. And if I run it again and give it a condition as overflow, like the values as 255 plus 14 and in 8-bit, then it shows us 255 itself, but overflow occurred in 8-bit arithmetic. The value doesn't change because it exceeds 8-bit. If you want to get the exact result, it needs to be converted to 16-bit or 32-bit to get the exact result. For now, it shows the result as 255 and overflow occurred. Now let's go to the second program. Program number 2 is about unsigned subtraction with underflow detection. What does this program do? This program subtracts two unsigned integers using 8-bit or 16-bit arithmetic and checks for underflow. If you go for the coding explanation, the first line is the same as it is, and in line number 3 and 4, we're getting two inputs from the user, unsigned integer values. Okay, and in the seventh line, we're checking the condition for 8-bit or 16-bit arithmetic. The user selects the bit width, and in the 8th and ninth line, inputs are converted to unsigned integers. And 10th line, the difference of the two values has been calculated. Unsigned subtraction is performed. And in the 14th line, if the first value is smaller than the second, underflow occurs. It is displayed as underflow occurred in 8-bit. The 15th line, or else no underflow in 8-bit subtraction. In unsigned arithmetic, underflow results in wrap around behavior, similar to how hardware ALUs work. Let's run the code and see the output. Let's put the first value as 10, second value is 2, and for 8-bit, the value is 10 minus 2 is 8, and no underflow in 8-bit subtraction. And if you go for underflow condition, like the first value should be less than the second value. So if I give 2 as a first integer, then 10 as a second integer, and for the 8-bit, the subtraction result will be shown as 0, but it will display as underflow occurred in 8-bit subtraction. The third program, unsigned multiplication with overflow check. What this program does? This program multiplies two unsigned integers using 8-bit or 16-bit arithmetic and checks for overflow. If you go for the code explanation, everything is almost the same. If you directly go to the 10th line, where the product of the two values is stored in the variable called as prod underscore val. Here, the two variables are multiplied using the symbol asterisk or star. As well as in the 14th line, the condition is being checked, like the first value and the second value's product is greater than 255. Displays that the maximum value exceeds or overflow occurred for 8-bit arithmetic, else no overflow is occurred. This illustrates why larger bit widths are required for higher precision computations in processor design. Now let's run this code and see. And I'll put a value, first value as 2, second integer value as 3, and it's 8-bit. And the result is, if you run it again for overflow condition, I'll put the value as sum of 50, like another 50, 8-bit. The values it shows us 255, but overflow occurred in 8-bit multiplication. Now let's go to the program number 4, basic unsigned subtraction. What this program does? This program demonstrates basic unsigned subtraction without explicit underflow detection. Basically, it doesn't check the underflow detection. That's it. So everything is almost the same. In the 11th line, it calculates the result as the difference between the first value and the second value, and it is displayed as 8-bit subtraction result. The result is displayed normally. And if underflow occurs, MATLAB automatically wraps around demonstrating unsigned arithmetic behavior. Let's run the code and see. I'll put the value as 3, second value as 2, 8-bit, and the result is 1. And if we go with the underflow, first value as 2 and 3 for 8-bit, and the result shows us 0, but it doesn't show us underflow detection because it's not mentioned, it's not required in this program. Now if you go to the program number 5 is unsigned division with division by 0 handling. What this program does? This program performs division while safely handling division by 0 errors. And almost everything same in the line number 7. If b is equals to 0, checks if the denominator is 0 or not. If it is 0, display the error as division by 0 is not allowed. So return and end. After this error is shown, it stops program execution to prevent undefined behavior. The result is calculated here as first integer value divided by the second integer value, performs unsigned division here. And in the 17th line, the result is converted back into the selected bit width. Memory usage is again calculated using the whos command in the 21st line. Now, that concludes the coding section of part 1 for computer organization and architecture. These programs demonstrate how low-level arithmetic operations can be simulated using MATLAB. They also highlight the impact of bit width on overflow, underflow, and memory usage. Thank you for watching.